Okay, well, I'd like to just take a few minutes and talk about solving the diet problem using CVXOPT, which is an optimization solver for Python. All right, so I know out there's going to be a lot of people who use Python because it's open source. Maybe I'm spoiled. I'm very familiar with MATLAB. Python, I just haven't had any need to use it all that much, so I'm definitely nowhere near the expert. Um, but I'm lucky to have graduated with my PhD from UCLA with actually one of the developers of CVXOpt. So I gave Martin Anderson a call today, and he just gave me a few pointers, and so that's what I'm going to show you today. Just a simple the code for solving the diet problem. Okay, so first let me go to their website. So here's the CVXOpt website, cvxopt.org, and you might be interested. For example, if we go to documentation, and then let's see if we go to user's guide. Here you have a lot of very interesting information. Okay. But down here, if I scroll down just a little bit under cone programming, you're going to see linear programming. Okay, so if I click on that, you're going to see that the LP is sort of an interface for cone LP. So it's sort of like an easier version of the cone LP. But we won't get into the cone LP. We're just going to use the simple LP solver. And as you can see here, there are two. You can see here there's a primal and there's a dual. Now we won't talk about the dual. We're going to focus on the primal, at least for now. Just like all the other problems we've been solving are the primal problem. Okay, so this might look just a little bit different than some of the other ways you've seen. Okay, some of the other forms, but it really is actually just if you've watched and you should have watched the forms, the LP forms and formulations and switching back and forth, then this should make some sense. Now, let me take a minute and show you why that should make sense. So let me write it how they had drawn it there. So it was C transpose X, subject to GX plus S is equal to H, and AX is equal to B, and S is greater than or equal to 0. Okay, so here's what I'm going to do. I'm going to do a little trick, and I'm going to, so we know S is greater than 0. So if I get rid of S, that isn't my variable that I'm trying to minimize. Or I should say that affects the cost function, just X is. And therefore I don't need this constraint. But of course, now that I've taken away positive values, this equals is no longer true, and what I get is a less than or equal to. Okay, so that really was just a slack variable. So really, that form is really an inequality form. Inequality constraints and equality constraints. And basically, their solver needs everything to be in equality form, so they automatically add slack variables as we have talked before in the LP formulations lecture. Okay, so that's all that really is. Now if I go back to it, you can see. So here's the form. Okay, and when we talk about duality, then this slack variable will come back into play, but at this point you could almost ignore it and just realize that is your inequalities and those are your equality. Over here to our diet problem.py, standing for Python, and for you Python users, you're going to be very familiar with this. So you can see that here we've imported CVXOPT, and we've imported a few a few libraries from CVXOPT, okay, that we're going to use. So we have a matrix and also a sparse matrix, that library that we imported, including, and of course, the solvers. All right. So here again, this is going to be very similar to my MATLAB code. I made a list of the names of the foods, so you can see their strings. And you can see that it's a little different than MATLAB. There's no semicolon, and this list is already assumed to be column vector, and it's spaced by or delineated by commas, okay, instead of semicolons, which is in MATLAB. And here's also the names of the 11 nutrients, okay. Now here's our big matrix A, which is going to be so this is actually, each one of these is a column. So this is a column of column. Let's see. Yeah, this is a list of columns, basically, okay, which makes a matrix. So this is 11, and then you're going to see you're going to have another 63, a total of 64 of these 11 lists, which refer to each food. Okay, so that's your 11 by 64 matrix right there. And then finally, just a little piece of Python. You'll see at the very end, we put here this TC equals D, the string D, and that tells Python that even this number here, this 4, you can see that it's not 4.0, which would tell it that it's a double precision. Python might think this is integer, so if you add this, then it will know that everything is a double precision number. Okay. Here's our cost vector. All right. Now you can see that it is one vector, okay, a column, and we'll do C transpose. And again, although this time the TC equals D double precision was unnecessary because of the decimal points, we left that in. All right. Now that here's the minimum nutrients, the double precision was necessary, and the max nutrients. All right. So this is basically the same as MATLAB. Now here, this piece of code is to make the identity matrix, so we need that. Of course, now we can make, since we have the A matrix, which is the amount of nutrients per food, that's our A. So here's our A, our minus A, and of course our minus identity. Now notice the identity was made with a sparse matrix, so I'll just suggest that you look at the user's manual to get a little bit more, but it basically says that you're going to put ones at the so the range is from 0 to 63, so at the 0, 0, 1, 1, 2, 2, so basically the diagonal, and this matrix is a 64 by 64 matrix. All right. And then finally we need the H, so we've got our Gx is less than H, our H are max nutrients minus min nutrients, and of course the 0 vector, which is a 64 by 1 vector with zeros in it. All right. And then finally we just solve it. Solvers.lp, the cost, your G, and your H, and you get your solution by this command. Okay. So finally, what we want to do is we want to spit out to the screen anything that is non-zero, and more specifically maybe any element of the solution X. Remember, this is X is the number of servings, that is greater than, practically 0, which is 1e to the minus 6. Okay. I would have said greater than 0, but in machine language, 1e to the minus 13 could be considered non-zero, so it's better to increase that number a little bit. And if there is a non-zero element for the number of servings, then this command says spit out the amount of the serving and the name of the food. Okay, so that's it. I'll share this code with you, and let's run it actually. So here I'm in my terminal on my MacBook, and I'm going to call the die.problem.py. So as you can see, here it is going through the iterations until it finally converges to an optimal solution. And here's our optimal solution. You can see I don't remember the exact numbers, but I'm sure they're the same. But I do recall this list of carrots, potatoes, skim milk, peanut butter, and popcorn as being our optimal meal for the day. Not that good. All right, so I'll leave you with that. Thank you.